got started with the worksheet. Any doubts and questions in projectile motion so far, people? No?
Sir, projectile motion we are learning, it is for 2D now. We are not using z-axis here.
We are not using, sorry, come again, what?
Z-axis.
Yeah, because see, you understood one thing, that projectile motion will always be two-dimensional in nature as long as there is only gravitational force acting. Because see, whatever oblique velocity you project it with, your initial velocity is one vector and your acceleration due to gravity is a constant vector, g is the other vector. So two vectors only define a plane, na, beta? You understood, na?
Yes, sir.
So, and that plane will always be vertical. You understanding my point, na? So whichever direction you point your initial velocity u in, if you consider that vector and you consider the acceleration due to gravity vector, those two vectors define a two-dimensional plane. And they define a vertical plane. So the motion is restricted to that plane. There is no second force that can bring it out of that plane. For example, if there was wind resistance or there was some other type of force like electrostatic force or something acting along with gravity, then there's a possibility that the object as it is moving in its trajectory, it comes out of that two-dimensional plane. But here that possibility is not there. You understood the point? Yes, is it clear?
Yes, sir.
So क्या होता है ना, we define the XY system such that your not only your x-axis is horizontal and y-axis is vertical, but when you resolve your initial velocity u into components now, its horizontal component is only along the x-axis. You've chosen your x-axis in such a way. So there is no need for the z-axis because the initial velocity does not have a z component. Okay, so the motion is restricted to that two-dimensional xy plane, which is defined by the initial velocity vector and the acceleration due to gravity vector. So that's why it's basically a two-dimensional motion, and not only it's two-dimensional, but it's a parabolic trajectory. It's a quadratic function between x and y. So it traces out a parabolic path in your two-dimensional xy space. Okay. Three-dimensional motion typically will be a situation where there is more than one force acting on the object, because otherwise, if there's only one force acting which remains constant, it cannot be three-dimensional, because again your u and a will define one plane. So only in a situation where the acceleration is variable because of multiple forces acting and all that, only in that kind of situation you can have a truly three-dimensional type of motion. And those things also we'll be discussing at a later stage. Okay, but as of now, our kinematics is restricted to projectile motion, in which there's this thing happening. Yes, Ishan, your example is very correct. I just saw in your in the messages that a football swinging in air. Yes, that becomes an example of 3D projectile motion, because the spinning action of the football actually creates something called Magnus effect. It creates a pressure difference between the it creates a pressure difference across the diameter of the football, because the spinning surface, okay, it makes air circulate in such a way that it creates a pressure difference. So it's quite an interesting phenomenon actually, which unfortunately we are not studying at this stage, but you can look it up on the web also. It's called Magnus effect, MAGNUS, Magnus effect. So the difference between the projectile motion of a non-spinning object versus a spinning object, particularly something which is which has a significant amount of viscous force or air drag type of force. So a football is something typically like that, because it's a it's a large size object which is hollow from inside, so it's low density in that sense. So compared to its weight, the air drag sort of forces become significant. Whereas if you take something like let's say a synthetic ball or a cricket ball, and you give that one spin, the spinning action has a different effect on it, but it does not affect the motion through the air all that much as a football, because it has much larger density. So its weight is much larger compared to any type of drag forces. So something like a cricket ball or a hockey ball, if you spin it and throw it in the air, it's not going to, okay. But yes, a basketball or a football, because it is hollow, so it has, as an object, it has comparatively low density. So that Magnus effect becomes very pronounced, that effect of air drag becomes very pronounced. And the moment you give it spin, that becomes even more significant from one side, okay. So as it is going in that parabolic kind of path, it also veers towards one side. Actually it veers towards the side you're spinning it on. So that's yes, that is correct. Okay, so very good. So this is a little bit about general information about types of motion other than our standard projectile motion. Okay, but then once again, talking about the standardized situation that we're talking about here, projectile motion, you're always restricted to that two-dimensional motion under the action of gravity alone. So that kind of thing. Okay, just a second, people. I think supposed to start the lecture for the non-integrated students also, right? Just yeah, so students of the non-integrated batch have also joined, right? I hope. Yes. So let's get underway. So this is our third session of projectile motion, right? What is it? Second session. Yeah, second session of projectile motion. I will come to the doubt questions from the worksheet also.
Sir, on 26th August, we have done projectile
second
motion session 2.
Yeah, so this is the third session, sir. Yes.
Yes, sir.
So we've discussed that projection from an elevated point in the last lecture. Yes. I think in the non-integrated batch, I might not have sent the notes of that, no? Yeah. Okay, I will forward the notes to the non-integrated batch group also. Okay. Right. So let's start with an quick recap type of question of projection from an elevated point. Okay. So we will look at a comparison of two such projections. One where we are projecting in such a way that the object actually gains height and then falls. And simultaneously, let's look at another projection where the angle of projection is such that the initial velocity has a downward component instead of an upward component. Okay, so we'll take a situation where both these heights are, let us say, 60 meters each. But in this case, on the left hand side, we are projecting like this. We are projecting with a speed of 25 meters per second, such that it has a vertically upward component, and this angle of projection is 53 degrees. Okay. As in the second case, let's say we are projecting like this. Now we have done a question like this in the last lecture. Okay. But this time I will ask a slightly different question here. Okay. And in this case, what we'll do is we'll find the maximum height from the ground level. Okay, so for case 1, we want to find the maximum height from the ground level achieved by the projectile. Okay. And the time t and the velocity at the instant when this height is maximum. Okay, that's what we're asking for the first case. And for the second case, we're asking a slightly different thing. We're going to ask what is the maximum speed achieved by the projectile. The value of this maximum value of time when the speed is maximum. Okay. In both cases, take g as 10 meters per second square. So you can think of it like a continuation of the problem we had done in the last lecture, you remember. Okay. So just start with this question, people, then I will come to your couple of doubts that people have asked from the worksheet also. Yes, Adinath. Yes, Manav, your answer is correct for the first one. Yes, Ashutosh, I will give you the list of questions at the end of today's lecture, which you can do from HC Verma. And then after today's lecture, you'll be able to do almost all questions in HC Verma except for the last few, which are relative motion based.
Okay, sir. Thank you.
Yeah. Okay, Manav, your answer for the maximum height from the ground and also the time at which it achieves that sorry, the velocity is correct, but just check your answer for the time, okay, at which it achieves this maximum height. It will be a different value.
Okay, sir.
Ah.
I'll check.
Adinath, you have got the time correct, but now see the maximum height that you've got now is from the projection point. Whereas in the diagram now, the question is clearly labeled that we are asking for the maximum height from the ground level. Okay, so you have to just add this height, this 60-meter height. That will give you the correct answer for what as per the question. I hope the point is clear, Adinath.
Sir, so my answer for maximum height was wrong.
Yeah. See, you are given the answer as 20 meters, no? So that is from the point of projection. So what we have to do, we have to actually now from that data or that value, we have to calculate the maximum height from the ground below. So that's going to become how much? 20 plus 60, right?
Yes. Sir, that's the answer for velocity.
Achha, V at maximum height. No, that is wrong, beta. That is the horizontal component. You maybe, achha, now I understood. Maybe you have done the resolution wrong. Just check your resolution of the vector.
Yes, sir.
That's why you got. It's 15 I cap and 20 J cap, not the other way around. Okay, so achha, now additionally in both these questions, we also want to find out this R and this impact speed and this time for both the questions. Of course, you'll realize for the second part, the impact speed is nothing but the maximum speed. So actually the first part is almost the same thing. You're calculating V max, which is nothing but this impact speed. Okay. So anyhow, let's get started with the first part. Okay. So see, when I'm projecting from that point with an oblique velocity such that I've got a vertical component, vertically upward component. So in such a situation, our reference frame typically should be such that our y-axis is upwards, not vertically downwards, because you can see the object is initially going upwards. So it's more convenient to take your reference frame accordingly, that you take your origin as the point of projection, but you take the y-axis as vertically upwards. Whereas in the second case, you can do the opposite. You can take your y-axis downwards because it was projected with a negative or with a downward component. So this u is 25 meters per second. This angle is 37 degrees. Okay. So when we are projecting, it's initially going up and then coming down. So this t equal to 0 situation. Oh, sorry, theta was 53. Yeah. We'll correction. Yes. Theta is 53 degrees. Okay. So this height is 60 meters. So this is where we have to be very careful about our resolution of vectors. Okay. U cos theta I cap plus u sin theta j cap. So this is 15 horizontal and 20 vertically upwards. This is our initial velocity. Whereas our acceleration is the acceleration due to gravity vector. So it is going to be minus 10 meters per second square j cap. Because we have taken our y-axis upwards. So once we've written these vectors correctly, you'll see the rest of the things are pretty simple. You can see that your horizontal component looks like this. Your ux is 15 and acceleration's x component is 0. So x coordinate at time t becomes 15t and x component of velocity is uniform at 15 meters per second. Okay, so this is something that should be very easy and natural for you to work out. Okay, in all of projectile motion cases. The y component, on the other hand, it has an initial value of plus 20, okay, but an acceleration of minus 10. Okay. So at time t, your y coordinate is 20t minus 5t square, and your y component of velocity is 20 minus 10t. So these two equations, okay, that represent position and velocity in component form, this is actually all we need conceptually to solve all the parts of this question, right? So now, for example, I want to find out this maximum height. When it's at some point like this, from the ground level, it is having a maximum height. So that maximum height I can say is basically h plus y's maximum. Okay. So if y is given like this, 20t minus 5t square, you can see that y's maxima is going to be this much, 20 meters. Okay. So the overall maximum from the ground is going to be 60 plus 20 or 80 meters. Okay. So here I've just directly used that formula. I didn't get into the derivation of the maxima because I know this already, that if this angle is u and this, I mean, this speed is u and this angle is theta, then from this horizontal level at which we have projected, this maximum height is how much? Is given by the formula u square sine square theta by 2g, or uy square by 2g. So that is this part. Okay. And then to that I've just added the height from the ground for that horizontal level. So this is the answer to the first part. Okay. And you can see that it reaches at t equal to uy by g. So that's going to be 2 seconds. And that is when our y component of velocity becomes 0. So at the highest point, the velocity will be just 59. The time will be 2 seconds. And that maximum height from the ground, as we've just calculated, is 80 meters. So this is the complete analysis of this part. Okay. Now, before we come to the second case, just use these same equations also to determine these other properties, that what is the impact speed when it comes and hits the ground? What is the time at which it hits the ground below? And also, what is this horizontal range r? So everything that you need is there in these 4 equations. You just need to see how to substitute the correct quantities here. Yeah, Adinath, so that is the point. Now, see, your y coordinate is reaching the maxima. So dy by dt should be 0, no? Dy by dt is the y component of velocity.
Yes, sir.
So that property holds, no? It's still a parabolic path. Doesn't matter that we have projected from an elevated point, but the trajectory is the same. So you know that it has to first ascend and then descend. So at the highest point, it's just transitioning from ascending to descending. So at that moment, the y component of velocity should be instantaneously 0. So that's how, in fact, we find out the time also, no? That is 2 seconds, because you're
Yes.
putting the condition that Vy is 0.
But if we
Yes.
use the formula to find time here, we will get 4 seconds.
No, beta. So, but that formula is based on what idea? That is the standard projectile motion case, no? So, according to that formula, what is your y coordinate becoming at that time of flight, capital T? It should be 0, no? Have you understood the point? That formula 2u sin theta by g, वो किस case के लिए है? When your y coordinate is becoming 0 at impact. But here it's not coming and hitting the same horizontal level, no? It's hitting the ground which is at a below horizontal level. So your y coordinate is not 0, right?
Yes, and
So we have to substitute a different condition in our equation. Which one? The equation for y versus time. Now, so in fact, what should be the y coordinate at the time of impact? Just from the diagram, tell me what should be the y coordinate.
time of impact 0.
नहीं बेटा यहाँ पे देखो, the impact is happening at this point. I'm labeling. You see now? And whereas what was your starting point? It was your origin here. So what is the y coordinate of this point?
60.
Huh?
60.
Minus 60 beta, because y axis is upwards, no?
Yes.
Okay, so that is the thing that you have to adjust now, because it's from an elevated point. Yes, very good. That's correct. Adinath, just the point I was making. You sent the correct message. Okay. So we have to substitute y as minus 60. So that will give us a quadratic equation for time. And one of the roots will be negative, one of the roots will be positive. So the positive root will in fact be the correct time. So next thing, we want to find capital T, we want to find R, and we want to find the impact speed. So the first thing is that at T equal to this capital T, or so-called time of flight, okay, your y coordinate should become minus h because it hits the ground. Okay, so from this equation above, we have y is equal to 20t minus 5t square. So minus 60 should become 20 capital T minus 5 capital T square. So this is a simple enough quadratic equation. Okay, so you can just divide it by 5 and make it like this. Okay. So you can see this has two roots. One is 6 and one is minus 2. So minus 2 will not be applicable. This will be the correct. Okay. So 6 seconds is the total time of the flight. So I'm just minimizing the screen, just go through the calculations from the beginning. Okay, we haven't finished this yet, but everything you need for the rest of it is here. That is for the impact speed and the range. Just use these values.
Sir, can you please scroll up for a moment?
Yeah. This part or the solution below?
No, sir, the question part.
Okay.
Thank you, sir.
Okay. Yes, very good, Adina, that's correct. Impact velocity, your value is correct. Q, the range will be Vx into time now. So time is 6 seconds. Okay, so let's see. So now you'll see that at t equal to capital T, which we have already calculated as 6 seconds, the value of the x coordinate is r. So x coordinate was how much? It was 15t. So here the range will become 15 into 6. Okay. So the horizontal displacement at the time of impact will be 90 meters. Okay. And also at this point of time, the x component of velocity will be u cos theta, which we saw was 15, but the y component of velocity is u sin theta minus gt, which here will be 20 minus 10 into 6. So that will be minus 40. Okay. So that's how the impact velocity, when you calculate, will come out to be 15 I cap minus 40 j cap in meters per second. Yes, Adinath, that's correct. Good. Okay, now move on to the second part. And the same concept has to be applied. The only difference is that you're projecting it such that the oblique velocity is sort of downwards. It has a downward y component or a vertically downward component instead of a vertically upward component. So to just make that adjustment. Okay, so people, I hope all the calculations in this part are clear to you. Now let's come to the second situation. So in this one convenient thing we can do is we can take our y-axis downwards this time. Okay, because our initial velocity's vertical component is downwards. So it will be more convenient to go that way. Of course, choice of reference frame is always up to us. There's no hard and fast rule, but I'm just saying this will be a more convenient way of handling it. So when we resolve the initial velocity vector, so again, it's that kind of situation. This is 25 meters per second. This angle here is once again 53 degrees. And acceleration due to gravity is like this. So we will take the initial velocity as 15 I cap plus 20 j cap again. But only this time 20 j cap means it's downwards instead of being vertically upwards. And that's why our acceleration vector will be 10 j cap instead of minus 10 j cap. So you can see that the particle does not ascend at all. Straight away it starts descending. Comes and impacts the ground at some point of time. So when it impacts, that is when the speed will be maximum. You can understand that as a sort of implication of work energy also. As it's descending, it is losing potential energy. So obviously it's gaining kinetic energy. Okay, so you can see that this will also be the maximum speed during this path. Okay. So these are this time downwards. Okay. So the y component of velocity is 20 plus 10t. So you can see the y component of velocity is increasing in magnitude. That's why all the time the speed is increasing. From this, your x component of velocity is constant. X component of displacement is proportional to time. So now use these equations to generate everything. Okay. No, Adina, the time will come out to be quite a simple value. Okay. It's very similar type of quadratic equation you'll have to solve. So this time, what should be the y coordinate at time capital T?
60.
Yeah, it's plus 60. So just substitute that over here. The y coordinate is h or 60. The x coordinate is r, and the velocity is the impact velocity. Okay. Starting with this, that yes, that's correct now. Yes, that's correct, Adinath. Yes, very good. Shivansh, your answers are also correct. R is 30 meters. Okay. No, Manav, see, you cannot use that formula T is square root of 2h by g, because that formula is when the initial vertical component of velocity is 0, na? When your uy is 0, that is when that formula is applicable, because half gt square is equal to h. So that particular case will not be applicable here. Hope you understood this point, Manav.
Yes, sir.
Yeah. So that would have been the case if we had projected it horizontally, but here we have projected it such that it has the initially downward component. So this is the applicable thing. So now at t equal to capital T, which is 2 seconds, the x coordinate is the range. So the range is going to be 15 into 2, 30 meters. Okay. And the y component of velocity is going to be 20 plus 10t, so plus 40. So the impact velocity is 15 I cap plus 40 j cap, which is incidentally the same thing as that first case. Now this is where we'll see something interesting, that they have a sort of symmetrical relationship. The first case that we discussed and the second case, I'll show you how that's the case. In the first case, if your parabolic trajectory was like this, if you do some more calculations, it's quite easy to show here that if it started from t equal to 0 here, it reached here at 4 seconds, and further it's reached the ground at 6 seconds. Okay. And it impacted the ground with a velocity which had horizontal component of 50 and a vertical component of minus 40. Here we have taken the y-axis upwards, of course. Okay. If you compare this with the second case, you'll realize that it's like a second part of this motion. Hence, you're getting that kind of value. Here, we projected it like this. That is actually this point. At this point, you'll see the velocity is 25 meters per second. And this angle below the horizontal, this is 53 degrees. So actually, this point actually corresponds to this point exactly. And the journey from here to here corresponds exactly the journey from this starting point here to this. So that is why it takes 2 seconds. Okay. And that is why the impact velocity here is the same. It's got a horizontal component of 15 and a vertical component of 40.
But in
Yes.
first case, y axis is upwards, and
Yeah.
second case, y axis is downwards.
Yes. So that's why we have written the impact velocity like this. It is 15 I cap plus 40 j cap. But it signifies the same thing, that it has a downward component of 40 and a horizontal component of 15.
Sir, so should we specify that we took y-axis downwards?
Yeah, of course. That we have specified in the diagram itself in the beginning.
Yeah.
So when we are writing this answer, it's already taken care of because we specified that in the diagram.
So we don't need to convert it back again like minus mein karke.
We don't, not unless we want to show both of them with a common reference frame. Here we are not doing that. We've drawn two different reference frames for the two cases. So that's not really necessary, right?
Okay.
Okay. Okay, now also want to discuss a couple of applications of equation of trajectory that we had discussed earlier. Okay. So you'll remember that we had discussed a secondary form of equation of trajectory where we wrote the equation in terms of the angle of projection and the range. Okay, now this is coming back to the standard situation of projectile motion, that is projection from a horizontal plane such that it's coming back and impacting that same horizontal plane. So that kind of situation. So if we project at u and at an angle theta, what we've seen is that in the xy plane, the path or the trajectory it follows is given by the equation y is equal to, in that secondary form, it was like this, x tan theta into 1 minus x by r, where r is this horizontal range. Okay. Now this theta is the angle of projection. So we will look at an example or two with the application of this concept also.
Sir,
Yes.
sir, in the last question where we had y equal to minus 60 and we had to find the range, that time this would not have worked.
This can still work, but the thing is, you have to understand that you have to modify this a little. Okay. So for example, here when we projected it like this, no. So our x component was 15, our y component in the downward direction was 20, and we had taken y-axis like this and x-axis like this. So we can write an equation that represents this path, this trajectory. As it's going from here, this trajectory will also be parabolic because it's after all the same motion, and we can use that equation of trajectory also. Okay, so what we can do is we got x as 15t and we got y as 20t plus 5t square. Correct? Remember these two equations?
Yes, sir.
So अभी क्या कर सकते हैं ना, to write this equation of trajectory, we want to write an equation which is satisfied by every point lying on its trajectory. No? So we have to eliminate time. So from here, substitute the value of t as what? X by 15. And you'll get that equation of trajectory. And you'll see that that's also a parabolic equation. It's like this. It might be a little lengthy, but we can still do it. So you can see we'll get y as 4 by 3x, correct? Plus this will be how much? X square by 225, but into 5. So that's
X square by 45.
X square by 45. We'll get this equation. So this equation is now this curve's equation. So for example, if I want to find something geometrical, like I want to find the range, you can see at this point, the x coordinate is the range and the y coordinate, which we don't know, whereas the y coordinate is the height, which we know, which is how much? 60 meters.
Yes.
So I'll substitute that here. That will directly give me the range. So I'll substitute y as 60 and I'll calculate how much x is. So it's a little lengthy and painful, but at the same time, this quadratic equation will give us two roots. One will be negative, which we won't take, and the other will come out to be plus of, what was the value we had got that? 30 meters, right?
Yes, sir.
Yeah. So it will come out to be plus 30. In fact, one nice way to check it is that just see if you substitute x equal to 30 in this side, if the left hand side matches the right hand side or not. We'll see it matches, so that checks that 30 is the root of this equation. So we can always generate an equation of trajectory like this for this type of case also.
Yes.
Okay, understood the point? Yeah. Okay.
Yes, sir. Thank you.
Okay. Now coming back to this thing, the standard case of projectile motion with equation of trajectory. Now again, I want to discuss a question where we are going to depend on the equation of trajectory and the symmetry. Okay. So what is given in the question is geometrical information. And remember, I told you that whenever the information given in the question is not time based, but geometry based, we are always well advised to use equation of trajectory. Okay, so that's what we'll do here. So in this question, a particular projectile motion is shown like this. Okay. And it is shown that when it is at a distance from here of, let's say, 40 meters, okay, its height is a certain value, so I'll tell you, and that height again repeats itself when this distance is 200 meters. That is the first information that is given. And this common height that these two have, this is given to us. Just give me a moment, I'll calculate it for you. Okay, so this is 35 meters, this height. Sorry, this is 25 meters, my mistake. We will make this height 25 meters. Okay, so from this, what we want to do is, we want to find the maximum height, the range, okay, the projection speed and angle. Take G as 10 meters per second square if required. So see how you can make use of equation of trajectory over here. Don't try to get into the time-based equations, because you can see that will really land you in a lot of trouble, because you'll have to find time at various, you'll have to assume some time t1, t2 at these 2 points and then eliminate them and all that. So it becomes a huge hang on. Okay.
Sorry, can you scroll up for a second?
Yeah. This part
Sir, that equation or trajectory part.
or that part? Okay. Yeah. The original equation of trajectory was this. It was x tan theta minus half gx square upon u square cos square theta. But as we saw, this is a very cumbersome way of writing it, and it does not really relate that nicely to numerical problems. So we reduce it to this by factorizing it and substituting r as this value. So then it becomes much easier to apply.
Yes, sir. Thank you, sir.
Okay. Adinath, it's tan theta is not going to be 25 by 40 beta, because see, the initial velocity vector is not lying along the hypotenuse of that triangle. No? It's a parabolic path. It's not a straight line path. Now, hint to you guys, see, at these 2 points, if the height is the same, let's say this time is T1 and this height time is T2. So at T equal to T1 and T equal to T2, if the Y coordinates are same, then what it means, they're symmetrical points. No? It means that the sum of the time should be time of flight, but more importantly, the sum of the X coordinate should be how much? It should be the range. So this is the hint I'm giving you. These 2 points over here, they are symmetrical points on the parabola. Okay, so basically what should happen is that this distance from here to here should be the same as this distance from here to here. Doesn't exactly look like that in my diagram, but in a perfectly drawn parabola, you see that this is the case. No? That straight away should tell you how to calculate the range. And then the rest of it you can see from application of equation of trajectory. Yes, very good. Adinath, now your answers are correct. All of the answers are correct. Projection speed, angle, range, maximum height. Okay, so from this fact here, you'll understand that the range is 240 meters. Okay. And once you understood the range is 240 meters, you can see that the equation of trajectory is x into some unknown tan theta into 1 minus x by 240. Okay, so theta is the unknown quantity here, the angle of projection. Now, if I just label this point here as A and this point here as B, you can see the point A, it has an x coordinate of 40, right, and a y coordinate of 25. And the point B similarly has an x coordinate of 200 and a y coordinate of 25. Both of these lie on the parabola. So they satisfy this equation. So they should satisfy the equation of trajectory. So that means that will give me the value of theta. And you'll see just the fact that I have two sets of coordinates is not going to give me any extra information. It's a quadratic equation. So you'll get the same value of tan theta for both the sets of coordinates. So for example, if I substitute E, you'll get that 25 should be equal to 40 tan theta into 1 minus 40 by 240. Now this is the same information that you'll get if I substitute B. Okay. That is 25 is equal to 40 tan theta into 1 minus 200 by 240. See, interestingly, both of these will give you the same information. This is 1 minus 1 by 6, so 5 by 6. So this is giving you tan theta is 3 by 4. This should also do the same. Okay. So this is going to be 200 into not. So you got this. Now directly in the equation of trajectory, you can use this fact that if you see the coordinate of the vertex point, this point has a coordinate x equal to r by 2 and y equal to h. Okay. So just make use of that to find the maximum height. H is equal to, now r by 2 is 120 and tan theta is 3 by 4. So your maximum height will become 120 into 3 by 4 into 1 by 2. So 45 meters is becoming our maximum height. And now just one of the standard formula you use, like for example, h is equal to u square sine square theta by 2g to find u. So 45 is equal to u square into sine 37, which is 3 by 5 square. So from that you will get u as 50 meters per second. So once again, for something like this, you can see equation of trajectory is a very logical and simple method to use. Okay, so these are again some examples of application of all these things: equation of trajectory, then we saw projection from an elevated point. Now we come to the very last part of projectile motion analysis, where we will look at projection done on an inclined plane rather than from a heighted point. We will look at projection on an inclined plane. So let's look at a situation like this. We have an inclined plane which is at, let's say, an angle of inclination, if you label as alpha with respect to the horizontal, and somewhere on that inclined plane we are projecting a particle or an object or whatever, such that it's kind of projected up the inclined plane but at an angle, and the angle of projection that is given is not with respect to the horizontal but with respect to the inclined plane, and the projection speed is u. So it will follow. Okay, so nothing is really different in that sense, because it's an oblique projection, and again it will be uniformly accelerated under the action of gravity. But the difference is, instead of coming back to the horizontal ground level, okay, it's coming and hitting a inclined surface. So to be able to do those calculations of its motion relative to the inclined surface, we have to change our reference frame. That is the only point. Okay. So if it is projected at time t equal to 0, let's say it impacts the inclined plane with some velocity vi, okay, at some time t at, okay, at a displacement along the inclined plane, which we'll call the range. It's like an inclined range now. That's a range along the inclined plane, and also during the motion at some point of time it will reach some kind of maximum distance from the inclined plane. So we want to calculate all these things. Okay, so let's do this as a numerical example only to begin with. So in this example, given that our alpha is 45 degrees, okay, beta, the angle of projection, is 37 degrees, then u is, let us say, 35 meters per second, g is 10 meters per second square, and we have to take root 2 specifically as 1.4. That is, we have to take it rounded off up to first place of decimal. Now we want to find out the value of this range, this time when it hits the inclined plane, and this, which is basically the maximum distance from the inclined plane. All these things we want to calculate. Okay, so just make a note of the situation, then we'll discuss about this. So here we will slightly change our approach, because we are calculating the range on the inclined plane and the distance with respect to the inclined plane. So how we'll change the approach is that we will take our x-axis along the inclined plane and our y-axis perpendicular to the inclined plane. So that's how we will change the approach a little bit. Okay. Like we do in the case of, application of Newton's laws for an object. When we draw the free body diagram for an object on an inclined plane, okay, we tend to take our axis, instead of horizontal and vertical, we take it along the inclined plane and normal to the inclined plane, or perpendicular to the inclined plane. So same way over here, we will take that sort of approach. Okay. what happens when we take that approach is our acceleration due to gravity G is going to get resolved into two components. Okay, so first of all, let's draw our coordinate frame or system of coordinate axes or reference frame, if you like, okay, for this given situation.
Sir, can you scroll up for 1 second?
Yeah.
Thank you, sir. Done.
Okay. Right. So here, as I said, that since we are calculating all these things in reference to the inclined surface, the distance, the range, and all that, so it will make more sense for us to take our x-axis as tangential or along the inclined plane, and our y-axis on as normal or perpendicular to the inclined plane, in this sort of manner. Okay. And of course, the origin as the point of projection. So now when we do this, not only do we have to be careful about resolving the initial velocity, it's going to be u cos beta I cap plus u sin beta j cap, but also resolving the acceleration. The acceleration is still g, which is acceleration due to gravity vertically downwards. But now you can see that this is our system of axis. So we'll have to resolve it just like you do in Newton's laws, free body diagrams for inclined surface problems. Okay, so if this angle with the horizontal for the inclined plane is alpha, then G is at that same angle alpha with respect to the vertical. With respect to the normal y-axis. So here, the acceleration's components it'll have a negative x component of G sin alpha, and it will also have a negative y component of G cos alpha. So this is the critical step. After this, the approach is more or less the same. So our x component of motion is such that ux is u cos beta. I'll also just put in the values that we have taken above. So that is 35 into cos 37. So that will become 28 meters per second. Okay. And ax is minus g sin alpha. So that is minus 10 sin 45. Okay. So that is minus 10 by root 2, which we can write as minus 5 root 2. So with the approximation, we can write that as minus of 7 meters per second square, because we are taking root 2 as 1.4. Now, similarly, the y component of motion, you'll see the initial velocity is u sin beta, which is 35 sin 37 degrees. So that this time you'll see will become 21 meters per second. And the y component of acceleration is minus g cos alpha, that is minus 10 cos 45, which will again work out to be minus 7 meters per second square. So based on these, now what you do next is you write Vx and Vy as functions of time, and write the x and y coordinates as functions of time. And from that, you'll be able to easily generate the required equations to find out these three quantities: the time of flight, capital T, or the impact time, you can say, the maximum distance, and the range. Okay. So note this down and just try to work out the step further over here. We'll discuss. Okay, so let's complete this. So first we'll write these quantities parametrically and then we'll substitute the numerical values. You're getting the time as 6 seconds. Let me just check. Yes, that's correct. Very good. Okay. So I'm just writing these equations parametrically. If you are into the numerical problem by now, just continue working on that. Okay. So Vx as a function of time will become u cos beta minus g sine alpha t, which here as an equation will become 28 minus 70. Okay, this is the x component of velocity, and therefore the x component of displacement will become u cos beta t minus half g sine alpha t square. So that again, as you can see, will become 28t minus 7 by 2 t square numerically. Right. Similarly, your y component of velocity will be u sine beta minus g cos alpha t parametrically. So numerically, this now becomes this much. Now, these are the four important equations: the components of velocity and the components of displacement as functions of time. Manav, I think you have used a more like maybe you have taken root 2 up to second place of decimal, but just approximate it as 1.4 up to first place of decimal. So you'll get the time as 6 seconds. Okay. And I'll just verify the value of range and impact velocity, Adina. Okay, so now let's understand the condition for that impact to happen on the inclined plane. The condition is, as you can see, the y coordinate should become 0 because we have taken our x-axis as the inclined plane. So when it's hitting the inclined plane, it should be back to the x-axis. So I'm getting different values of range from all of you. So let me just verify. Okay. So first of all, you can see that from the diagram, you can refer to this, that at time capital T, the y coordinate should be 0 because it hits the surface, and the surface is our x-axis. Okay. So we've just seen that y as a function of time is this much. So 21 capital T minus 7/2 t square should be 0. So this is easily factorizable. So one root is 0, which is obviously not the case. That's the initial time. The other root is 21 divided by 7/2. So that is 42/7 or 6 seconds. Right. So that shows us that the time of flight is 6 seconds, or the time at which it impacts is 6 seconds. Now, again, at this particular time, capital T, the x coordinate is equal to r. So x as a function of time was what? It was 28t minus 7/2 t square. So r should be equal to 28 capital T minus 7/2 capital T square. So 28 into 6 minus 7/2 into 6 square. So what we can do here is we can take 42 common. Okay, so we'll be left with 4 here minus 3. So I think you're getting the range as 42 meters. Yes. Oh, is it 3/2? Sorry, 3/2. So the range is 42 multiplied by 4 minus 1.5. So that's 2.5. So 21 into 5, 105 meters. Just check my calculation, people, but this is the approach. Just check the last arithmetic calculation if it's correct or not. But oh wait, this should be 3 only, no? Here, not 3/2. Okay, so we will get it as 42, as I said. I've taken 42 common from this bracket, so I'm left with 42 into 6/2, so that's 3 only here. So the answer should be 42 meters. Yes. Okay. And now same way I'll calculate the impact velocity also by just substituting the time as 6 seconds for both the components Vx and Vy. Remember, in this case, x component is not constant because we have taken the inclined axis. Yes, Adina, that's exactly the point. Now, see, what we calculate over here will always be with respect to the reference frame that we have chosen. In other words, the choice of X and Y axis. Now, in the geometry of the question itself, we want to calculate quantities with respect to the inclined plane, like the maximum distance from the inclined plane, the range along the inclined plane. So we have to go with that choice of reference frame now. Okay. So that when we calculate the X coordinate at a particular point of time, we are calculating the displacement along the inclined plane. When we calculate the Y coordinate, we are calculating the distance from the inclined plane or the perpendicular distance from the inclined plane.
Yes, sir, but the velocity which we would get in I cap and J cap, if we had to find it with respect to the normal plane with which the angle alpha is forming, so then what we'll do?
Oh, then it becomes a big job, because we have to transform it. It's
Yes,
like
sir.
we are calculating the velocity where the components are with respect to the inclined axis, and we know that that inclined axis is at in this case in that it's at beta equal to 45 with respect to horizontal and vertical. So we'll have to recalculate it. We have to calculate the magnitude of the velocity, then see what angle it's making with the horizontal, and then recalculate the component. So that becomes a big job if we have to do that. Okay. But typically we won't really need that, because even if we have to calculate the angle and all that, it will be with respect to the inclined surface, not with respect to horizontal and vertical.
Yes, sir.
Okay. So our answers in this case will always make more sense if they are with respect to this kind of reference frame.
Yes, sir. Thank you.
Okay. Okay, so hope you've checked the calculation for this R, this range, it's coming correct, right? Okay, now moving on to the calculation of the impact velocity and also the maximum distance from the inclined plane. Okay. So you can see that again at t equal to capital T, which we worked out to be 6 seconds, the velocity is the impact velocity. So this impact velocity will have an X component of 28 minus 7t. So interestingly, it's having a negative X component. Now that might be a little confusing initially how the X component can be negative, but we'll understand the geometry of the question and it makes sense. Okay. So 28 minus 42, that's going to give us how much? Minus 14, right? And the Y component of velocity expectedly should be negative. Let's see how much that is. So this is minus 21. So the impact velocity in our reference frame is minus 14 I cap minus 21 J cap in meters per second. Now let's understand what this means. Okay, this negative X component that we're getting, how can we justify it geometrically, how that's exactly happening? So it's a situation like this, our inclined plane is at 45 degrees. This alpha was equal to 45 degrees and we projected it at 37 degrees like this. So it probably went like this, and then on its way down, we just do a better job of drawing this. Yeah, so 37 won't exactly look that small as an angle, slightly larger. So this is 45 degrees. Now this angle, I draw it as 37 from the inclined surface. So it's like this. Okay. So what it's doing is going up like this. And on its way down, when it is impacting, see the impact point, the velocity seems to be something like this. Okay. Now you can easily see that it's making an obtuse angle here. This angle is obtuse. That is why I'm getting a negative X component, because this is my X axis and this is my Y axis at this point. So it's like this. So that is the significance of this being a negative quantity here. So that's that. Okay. And now we also want to find the maximum distance from the inclined plane. So at any point of time in between 0 and capital T, if the coordinates are x comma y, you can see the y coordinate is nothing but the distance from the inclined plane. So the maximum distance is nothing but the maxima of the y coordinate for the given projectile. So y coordinate as a function of time, you'll recall, was 21t minus 7/2 t square. Now we just need to calculate the maxima of this. So just work this out next. Yeah, Adinath, I'll verify your answer. I think it's correct, 31.25. Okay. So you see that if you just factorize this, no, this is 21 minus 7/2 t. So you can see that this is again that parabolic kind of shape. If you think of the graph of y versus t, so it increases first and then decreases. So when it decreases, it becomes 0 at t equal to capital T, which is 6 seconds. So you'll obviously reach the maxima at the midpoint of this at t/2, which is 3 seconds. So that is going to be the maxima. Okay. So y's maxima is going to be the value of y at 3 seconds. So just substitute that 3 over here. So 3 into 21 minus 21/2 हो जाएगा ये, right? So that is correct, 63/2 or 31.5, sorry, not 31.25. So 31.5 meters is going to be that maximum distance.
Sir,
Yes.
sir, we can also use that na uy square by 2gy.
Yes, you can do that also. Very good. You can use that because basically you can use the idea that when y reaches the maximum value, okay, dy by dt should be 0. That means v's y component should be 0. Okay, so now you have this relation that vy square is equal to uy square minus 2g cos alpha into s, no? Or into y. Okay, so in this you substitute vy as 0. So y becomes how much? It becomes that maximum displacement or the maximum distance. So that becomes uy square by 2g cos alpha in this case. Okay, and uy was u sine beta. So this will become u sine beta was 21. Okay. And g cos alpha itself was 7. So that will work out to this. So this is also an alternate approach of working this out, right? Okay, so hope these calculations are clear. And now we'll quickly do another version of this question. Okay, this time we will see that we are projecting the particle or the object, whatever, from somewhere slightly above, and it's coming down the inclined plane. Let's take that kind of situation. And let's use slightly different values also. So this time our alpha is 30 degrees. And let's say we project something like this. So let's say we project it at 45 degrees. And our projection speed is 28 meters per second. So it has this kind of path. So again, we want to find out all those things. We want to find out the range, the time at which it impacts, the impact velocity, and the maximum distance. So once again, we'll take g as 10 meters per second square, and we want to find out all these things. Okay, just give this a try. Okay, now just again think logically how you should adjust your reference frame over here, how you should take your x and y axis to make this quite simple in terms of resolution and calculation of these quantities. Okay, so let's work this out. So we'll take this as our x-axis this time, right? Down the inclined plane, parallel to it. Right? We'll take normal to it as our y-axis. So let's right away express the component form of all these things. So y, x, u you can already see over here. Now I'll also include the acceleration due to gravity vector g, so that we can resolve that quite easily. This angle is 30, right? So our initial velocity will become u cos, I'll label this angle as beta. So 28 by root 2, or so you can write that as 20. And our acceleration due to gravity, we'll have to resolve it as g sine alpha I cap minus g cos alpha j cap. So it will become 5 I cap minus 5 root 3 j cap in meters per second. So we'll take, just like we have taken root 2 as 1.4, we'll take root 3 as 1.7 later. Yes, good, that's correct. Right, so our x component of motion is like this. And our y component of motion is like this. So at t equal to capital T, y is 0. So 8 by root 3 seconds. And our x coordinate is equal to r. So r will become 20 into 8 by root 3 plus 5 into 8 by root 3 whole square.
By 2.
5 into 64 by root 3 whole square, that is. Yes. So whatever this final value, this is going to be the range.
Sir,
Yes.
sir, 5 by 2 into 8 by 3 square. 8 by root 3 square.
Also 5 by 2, no? Right. So there is another factor of half here. So this will become 160 by 3. Okay, clear now so far? Now the impact velocity. So the y component will be minus 20. So the impact velocity something like this. And now we have y as a function of time, which we've already written before. 20t minus 5 by 2 root 3 t square. So d max is basically y is maxima, which will be the value of y at t equal to 4 by root 3 seconds. Because at 8 by root 3 is becoming 0. So again, that logical kind of method. Yeah, we can write the range very conveniently like this also. It is so I'm just minimizing this a little, people, and with this we conclude today's lecture. Next lecture that I have, I'll keep aside the first half of the lecture completely for your questions and doubts. So after today's lecture from H.C. Verma, kinematics section, you can do questions up to question 44. Okay. So you'll see that in this from about 1 to question 24 is one-dimensional motion. And then from about 25 to 44 or so is projectile motion in general. There are few questions in between where there is relative motion can be used, okay, but not necessary, not in this part. It's only in the questions after 44 that the situation gets a little bit more complicated. So we have to compulsorily use equations of relative motion, which we'll be studying in a later lecture. Okay. So next time we will mostly look at winding up doubts and questions and those sort of discussions from this section, so that you are well prepared for your major test coming up after that.
This is from the exercise section, no?
This is from the H.C. Verma exercise. Yes, the subjective exercise. Yes, Manav, to answer your question, everything we've discussed today will be part of your MT4 syllabus. Okay. So projectile motion with respect to inclined plane is also part of that.
Okay, sir.
Okay, so that's it for today's session, people. Wish you all the best. Thanks for attending. Have a nice day.
Thank you, sir. Bye, sir.
Thank you, sir.
Bye.
Bye, sir.
Bye.
Bye, sir. Thank you.
Thank you, sir.
Thank you, sir.